Okay, welcome to lecture number 34 of our course on fundamentals of transport processes. We were looking at the solution of the diffusion equation. As I told you in the last class, we derived conservation equations for mass and energy. All of these had a common form, the time derivative of concentration plus divergence of the mean velocity times concentration is equal to d times the Laplacian of concentration, where d is the diffusion coefficient, plus any sources or sinks of constant mass. Similar equation is obtained in the case of energy, except that you substitute temperature instead of concentration and thermal diffusivity instead of mass diffusivity. The Peclet number is the ratio of convection and diffusion in these problems. If I scale all lengths by characteristic length and all velocities by characteristic velocity, then I get a dimensionless equation of the form the Peclet number times the time derivative plus the convective terms is equal to the diffusion term plus any source or dissipation of energy. And the Peclet number is small, the ratio of convection to diffusion is small. And in the leading approximation, we neglect the convection of energy altogether, and we are left with solving the diffusion equation. D del square C plus any source of energy is equal to 0. So, this is the solution of the diffusion equation for the case where diffusion is large compared to convection. And first, we had looked at ways of solving it by separation of variables. In spherical coordinate system, the 3 coordinates are r, the distance from the origin, theta, the azimuthal angle made by the radius vector with respect to the z coordinate, and phi, which is the angle along the xy plane. We used separation of variables, okay, and from symmetry conditions we got discrete eigenvalues. In the phi direction, the requirement that when you go around by an angle 2 pi, you come to the same location means that the solution for the concentration should be identical when you go around by an angle of 2 pi. That means that this constant, the constant minus m square in the equation for the phi coordinate, m has to be an integer. Okay. So, this gives us a set of discrete eigenvalues in the phi direction, and the associated eigenfunctions or basis functions are sine and cosine functions in that direction. In a similar manner, we solved the equation for the theta coordinate, okay. And in this case we got solution in terms of the Legendre polynomials. Okay. The equation that we ended up with in the theta direction was the Legendre equation, and the solutions for this were in terms of the Legendre polynomials, okay, in the theta direction. And I showed you by means of a series solution that if the polynomials are to be finite both at theta is equal to 0 and theta is equal to pi, or at x is equal to minus 1 and x is equal to plus 1, the constant in the equation has to be of the form n into n plus 1. Okay. Okay, so the convergent solutions for this equation can be obtained only for discrete eigenvalues of this problem, from the requirement that the solution has to be finite both at x is equal to plus and at x is equal to minus 1. And so, we got these Legendre polynomial expansions. Okay. And I had written down the first few polynomials for you, and the product of theta and phi gives you functions of theta and phi which are called spherical harmonics. P n m of cos theta times sine and cos of m phi. Okay. These are orthogonal to each other when the inner product is defined as integral sin theta d theta from 0 to pi and integral over phi from 0 to 2 pi. So, these form an orthogonal set of polynomials. If you multiply one polynomial with another one and integrate, you get 0. You get a non-zero result only if you take the inner product of two identical polynomials. And then we solve for the the radial coordinate, and we got equations, we got solutions which are in terms of power laws with respect to the radius, r power plus n and r power minus of n plus 1. Okay. So, that gave us the final solution for the spherical harmonics for the solution of the diffusion equation in a spherical coordinate system. This is a series summation, n is equal to 0 to infinity, and m goes from minus n to plus n. So, for every value of n, you have m going from minus n to plus n. That means that there will be 2n plus 1 such solutions. So, if n is equal to 3, when you go from minus 3 to plus 3, you have minus 3, minus 2, minus 1, 0, 1, 2 and 3. So, 7 solutions for each value of n. Okay. So, this is the series solution, the separation of variable solution for the general case for any coordinate system. The coefficients in this are evaluated ultimately from the orthogonality conditions. I showed you that the particular case of the heat conduction from a sphere, which we had solved some time back in one dimension, is just the solution for n is equal to 0 and m is equal to 0. This is spherically symmetric. So, y 0 0 is just equal to 1, it is independent of theta and phi. And then we did the example of the effective conductivity of a composite. In this case, there is a spherical particle of conductivity Kp in a matrix with conductivity Km. Far away from the particle, there is a linear temperature gradient. The temperature has the form Tc plus T prime times Z, where Tc is the temperature at the center of the particle. And in order to determine the effective conductivity, one has to calculate the correction to the heat flux due to the presence of particles. So, one has to calculate what is the actual heat flux within a particle when it is placed in this linear temperature gradient. The temperature gradient has the form T prime. So, the temperature goes as T prime times Z far away. So, as if the temperature goes as T prime times Z, that means that T prime times Z is equal to T prime or P1 of cos theta. Okay. And I had shown you that because the temperature far away has symmetry 1 0, that is this P1 0 of cos theta, far away the temperature has this P1 0 symmetry. Okay. There is no forcing with respect to the temperature field for any other symmetry form. The only forcing for the temperature field is due to the 1 0 symmetry. Therefore, the solutions will also have that same symmetry in this particular case. Therefore, I can just write down the solutions with n is equal to 1 and m is equal to 0 and evaluate those coefficients alone. As I showed you in the last lecture, all other coefficients turn out to be identically equal to 0. Okay, for n is greater than 1, all other coefficients turn out to be identically equal to 0. Only the coefficients 1 0, that is AP1 and BM1, turn out to be non-zero. And from that I can straight away evaluate what is the correction to the temperature field due to the presence of the spherical inclusion. And we briefly discussed the spherical symmetries, we will come back to that a little later. Okay. And then I had defined for you the delta function, non-zero only when x is equal to 0, it is 0 for all x not equal to 0, and the area under the delta function is equal to 1. it is given by the limiting form of this function, which is 1 over h between minus h by 2 and plus h by 2, 0 otherwise, in the limit as h goes to 0. So, this function becomes taller and taller as h becomes small, it becomes thinner and thinner in such a way that the total area is a constant. And if I multiply this function by any other function g of x and integrate, it just picks out the value of that g at x is equal to 0. So, briefly, these are the properties of the delta function. This is a one dimensional delta function, has dimensions of inverse length, because integral dx times delta x is equal to 1. So, delta of x has dimensions of 1 over length. It can be extended quite easily to 2 and 3 dimensions. Okay. I just extend the definition. This function is equal to 1 over h square for minus h by 2 less than x less than h by 2 and minus h by 2 less than y less than h by 2, and it is equal to 0 otherwise. Okay. Is the delta function of x and y is the limit as h goes to 0 of f of x and y. And I plotted the form of this function for you. It looks like a cube whose height goes to infinity and whose area of cross section goes to 0. And this has dimensions of 1 over length square. Okay. And finally, we came down to the 3 dimensional delta function. This is non-zero only within a cube of side h at the origin. It is 0 everywhere else. The total integral over the entire volume of delta of x times the volume is equal to 1. And once again, it picks out the value of the function at the origin itself. And I showed you that the solution for the heat conduction equation for a point source T is equal to q by 4 pi k r is also a solution for the differential equation k del square t plus q times delta of x is equal to 0. Okay. So, the solution of this diffusion equation is identical to the solution for a point source at the origin, where the heat coming out per unit time is equal to capital Q. Okay. And I showed you that by actually solving this for non-zero value of x and then equating the total flux coming out to the heat generated per unit volume. So, this is a point source. Okay. The solution for a point source is temperature is equal to q by 4 pi k r. And I told you that if you had multiple sources, one can use linear superposition. If you have multiple sources, one can use linear superposition to write down the temperature field due to each of these point sources. You cannot do that for finite objects. You can do it only when there is a point source, and that is why the concept of a point source is such a powerful concept. Okay. If you had finite objects, if you try to do linear superposition, you have to make sure that all the boundaries remain the same. You cannot change the boundaries. Whereas, since the point source is an object of 0 dimension anyway, it does not matter whether the boundary exists or does not exist. Okay. So, for that reason, one can work with point sources and sinks quite easily in a manner that is not possible with finite sized objects. And one can write down the temperature field due to a distributed source in terms of temperature fields due to point sources. Okay. I showed you how to do that. You divide the entire distributed source, that volume, into small differential volumes, each of which is emitting q times delta V. Q is the energy per unit volume per unit time. So, q at the position x times delta V, q at the position x1 times delta V1 gives you the total energy coming out per unit time within the differential volume delta V1. Okay. And similarly for q at the position x2 times delta V2. As you make the sizes of the volumes smaller and smaller, this approximates a distributed source. Okay. This gets closer and closer to a distributed source. Therefore, you can add up the temperatures due to each of these individual sources, and in the limit as delta V goes to 0, you can convert this summation into an integral. So, for this system, t at the location x is equal to integral over x prime. Note that here x prime is the location of the source points. Okay. These are x prime, and x is the location of the observation point, the position at which you are measuring the temperature field. Okay. And basically what you are doing is you are adding up the temperature field at this location due to each of these individual small sources. Okay. Adding up the source, the temperature field due to each of these sources, and integrating over the entire volume to get the final solution for the temperature field. Once again using linear superposition, because you have reduced each of these sources to just point sources. And in the last lecture, we did an example of how one would use this for a concrete example of a wire emitting heat. Okay. So, I had shown you that in this case, I can define the source as a delta function in the x and z coordinates. Okay. And once I do that, I can use the property of delta functions that it picks out the value of the function at x and z is equal to 0 to actually get an analytical solution for the temperature field. Along the x z plane for y is equal to 0, this had a simplified form. However, one can actually plot out the temperature numerically using this more complicated form. Okay. So, this is the actual temperature field, and for any value of x, y and z, one can find out what is the temperature. For the particular case along the x z plane, I had simplified this and then further consider two different limiting cases. One is where r, the distance from the source, is large compared to the length of the source itself, L. If I am sufficiently far away from this wire, then it effectively looks like a point to me, a point, and the only the details of the point are obscured because of the distance from the source. The only thing that determines the temperature far away is the total amount of heat generated by this point source. So, the solution that I get will depend only upon the total amount of heat generated by this point source. The source was q per unit length per unit time. The length of this wire was 2L, therefore, the total heat generated per unit time is 2QL. So, the temperature is 2QL by 4 pi Kr. So, this happens when the distance from the source is large compared to the length of the source itself. In the opposite limit, where the distance is small compared to the length of the source, I get a logarithmic function. Okay. The solution is log of r. I told you that that is the solution of the equation in 2 dimensions in a cylindrical coordinate system for a point in 2 dimensions or for an infinite line in 3 dimensions. When I am sufficiently close to the source, it looks effectively like a source of infinite length. When the distance of the observation point from the source point is small compared to the length of the wire, then it looks effectively like a point, like a infinite line in 3 dimensions or a point in 2 dimensions. And for a point in 2 dimensions, the solution is a logarithmic function. Okay. So, this gives us an example of how one would calculate the temperature field due to a distributed source, in this case distributed along a line in terms of the temperature field for a point source. Okay. So, let us now look at a different kind of temperature field. Okay. In a Cartesian coordinate system, if I have a source plus q, okay, at a location at a distance L from the origin along the z axis, and I have minus q at a distance minus L. Okay. So, I have two sources, one plus q on the plus z axis, the other minus q on the minus z axis. Okay. Both sources of equal strength, one is positive, so it is a source of heat, the other is negative, and so it is a sink of heat. Okay. Now, if you go sufficiently far from these, if the distance x, okay, this is the x vector. So, if the distance r is sufficiently far from this, there is plus q generated by the source, minus q, that is heat is absorbed by the sink. So, there should be no net flow of heat sufficiently far from this source. Okay. So, what is the temperature field due to this combination of one source and one sink? Okay. The temperature field x. Okay. So, there is a source at the location at 0, 0, L. Okay. There is a sink minus q at 0, 0, minus L. Okay. And the combination of these two determines what the temperature is. Okay. So, T is equal to q by 4 pi k into x minus x s. And then there is this is the point x s of the source, and this is the point x s prime of the sink. So, I have minus q by 4 pi k. Okay. So, there is a generation of heat due to the source and an absorption of heat due to the sink. And at this location the distances, okay, this is the distance from the source, and this one is the distance of the observation point from the sink. Okay. So, the combination of these two is what gives me the temperature at this particular location. So, I know the two locations of the source and the sink at 0, 0 plus L, x is equal to 0, y is equal to 0, z is equal to plus L, as well at x is equal to 0, y is equal to 0, and z is equal to minus L. Okay. So, this becomes q by 4 pi k into 1 by square root of x square plus y square plus z minus L the whole square minus 1 over square root of x square plus y square plus z plus L the whole square. Okay. So, this is the total temperature field due to the combination of the source and the sink. Okay. Now, let us take the case where the distance from the origin is large compared to the distance 2L between the source and the sink. Okay. So, let us take the case where the distance of the observation point is large compared to the separation between the source and the sink. Okay. Okay. In that case, I can expand in L over R. Okay. That is when the distance r from the origin is large compared to the distance between the source and the sink. Okay. So, this temperature is q by 4 pi k to 1 over square root of x square plus y square plus z square minus 2 L z plus L square minus so just expanding out the z minus L and the z plus L. Okay. Now, I know that this square root of x square plus y square plus z square is equal to r square. Okay. In the spherical coordinate system, r square is equal to x square plus y square plus z square. Okay. So, this can be written as q by 4 pi k times 1 over square root of r square minus 2 L z plus L square minus 1 over square root of r square plus 2 L z plus L square. Now, this I can rewrite by taking out r as the common factor. Okay, I can take out r as the common factor to get q by 4 pi k r into 1 by 1 minus 2 L z by r plus L square by r square per half minus 1 over 1 plus 2 L z by r minus L square by r square per half. And I can use a binomial expansion for this in the limit where the distance is in the limit where L is small compared to r. Okay. Recall that I want to expand in this small parameter L over r. Okay. So, this becomes equal to q by 4 pi k into 1 plus half 2 L z by r plus plus terms of order L square by r square minus 1 minus half 2 L z by r plus terms of order 1 over r square. Okay. It's equal to q by 4 pi k r into 2 L z by r. I should take this as r square. Okay. So, this is the final solution that I get. Okay. This is equal to, I'll just rewrite it a little bit, 2ql by 4 pi k into z by r cubed. Okay. Or if I write this in a spherical coordinate system, I can use the substitution z is equal to r cos theta. Okay. So, this will become 2ql by 4 pi k into cos theta by r square. Okay. Rewriting this once again, 2ql by 4 pi k into p10 of cos theta by r square. Because p10 of x is just equal to x. So, p10 of cos theta is just equal to cos theta itself. Physically, what does this mean? Okay. Let us go back and recall our earlier solution for the temperature field that we had obtained by separation of variables. T is equal to summation a m n summation n is equal to 0 to infinity summation m is equal to minus n to plus n a m n This was the solution that we got from the spherical harmonic expansion. Okay. You can see that this solution is identical to this solution for n is equal to 1, okay, identical to this solution, constant by r square. For n is equal to 1, you will get some constant divided by r square, and m is equal to 0, you will get p10 of cos theta. Okay. So, the solution that we got from a source and a sink separated by a small distance is the same as the spherical harmonic expansion for n is equal to 1 and m is equal to 0, provided the two are separated along the z axis. Okay. So, this source and sink combination is what is called a dipole. Okay. There is a source and a sink that are very close to each other. The distance of separation is small, okay. And because of that, there is no net flow of energy. The sum of the combination of the source and the sink results in no net energy coming out, because Q is generated by the source, Q is absorbed by the sink. If you go sufficiently far away, there will be no net energy coming out. Okay. No net energy coming out means that the temperature cannot decay as 1 over r. Because if you recall, when the temperature decays as 1 over r, the heat flux goes as 1 over r square. Surface area increases proportional to r square. So, therefore, there will be a flux that is a constant. However, if you have a source and a sink close to each other, there can be no net flux. That means the temperature field cannot decay proportional to 1 over r. It can decay faster, 1 over r to some higher power. In this particular case, for this combination of source and sink, the energy, the temperature decays as 1 over r square. This thing here, okay, previously for a source I got Q by 4 pi k r. Okay. In this case, I get 2Q times L. Okay. Q is the source strength, 2L is the distance between the source and sink, and this 2QL is the dipole moment. Okay. So, this is only for decaying harmonics. This formulation cannot be used for growing harmonics. Okay. So, this is a physical interpretation of the terms in the spherical harmonic expansion. N is equal to 0, there is only 1. M is also equal to 0. That represents a source in which there is a net energy flow out from the origin, from the source. Okay. If you have a combination of a source and a sink, there is no net generation of energy. That means that the temperature has to decay faster than 1 over r. If you have a combination of a source and a sink, then the temperature decays as 1 over r square. And the dipole moment has dimensions of energy per unit time times length. Okay. Because that dipole moment by 4 pi k times p10 of cos theta by r square is the temperature field due to this dipole. So, this was for n is equal to 0 and m is equal to, for n is equal to 1 and m is equal to 0. As you know, there are 3 solutions at n is equal to 0, for m is equal to minus 1, 0 and plus 1. For m is equal to 0, we had a dipole that was aligned along the z axis, that is, the separation between the source and the sink was along the z axis for m is equal to 0. Okay. One could solve equations for n is equal to 1 and m is equal to plus or minus 1. Okay. 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 For n is equal to plus 1, one will get the solution as t is equal to 2ql by 4 pi k into sin theta cos phi. by r square, okay, is equal to 2ql by 4 pi k into p11 of cos theta cos phi by r square. Okay. So, for n is equal to 1 and m is equal to 1, the solution is a source and a sink separated along the x axis. For n is equal to 1 and m is equal to 0, it is along the z axis. And the final one for n is equal to 1 and m is equal to minus 1, the temperature field in that case is equal to 2 q L by 4 pi k sin theta sin phi by r square. Okay. So, this gives you the physical interpretation of the terms for n is equal to 1 in the spherical harmonic expansion. N is equal to 1 and m is equal to 0, a dipole separated along the z axis. Minus 1 plus 1 are dipoles separated along the x and the y axis. Okay. And there are only 3 ways to separate them, along the x, y or the z axis. Therefore, there are 3 terms, okay, 3 dipole terms. These are vectors, these are what are called dipole moments. Okay. They have a direction associated with them. That direction is the direction of separation. Okay. So, plus 1 and minus 1 are basically the dipole moments where they are separated along the x and the y axis. Okay. So, that is the interpretation of the dipole terms for n is equal to plus and minus 1. The next higher terms are what are called quadrupole terms. If you recall, the source, there was a net source of energy coming out, okay, from the origin. The dipole terms were a combination of a source and a sink in such a way that the total amount of energy coming out is identically equal to 0. However, there was a net dipole moment for that is the source and sink were separated by a small distance. In the limit as L goes to 0, okay, recall that when we calculated the temperature field due to the dipole, we took an expansion in L by R. That means that the separation of the source and sink was going to 0 compared to the distance from the origin. That is, the separation between the source and sink was small compared to the separation between the observation point and the dipole. So, in the limit as L over R goes to 0, the source and sink are coming closer and closer to each other. Okay. Even though the source and sink are coming closer and closer to each other, L is going to 0. However, this dipole moment 2qL has to be a constant. Okay. So, that means that Q has to increase, L has to decrease in such a way that the product Q and L remains finite even in the limit as L goes to 0. Okay. So, you get a dipole when you have a source and sink, the separation between those two goes to 0, the amount of heat generated or absorbed goes to infinity, the product of the two remains finite. In that limit, you get a dipole. The temperature field for that dipole decreases as 1 over r square when you go far away. Okay. And it can have 3 different alignments. One is along the x, the other is along the y, and the third is along the z axis. Okay. And that corresponds to the 3 solutions for n is equal to 1, m is equal to minus 1, 0 and plus 1. So, there are 3 solutions for the dipole moment. The next higher term is what is called a quadrupole. Okay. Okay. This is the spherical harmonic expansion for n is equal to 2. Okay. You have 2 sources and 2 sinks, okay, of equal strength Q, okay, arranged so that net source is 0 and net dipole is 0. Okay. So, for example, in this case for n is equal to 2, m can vary between -2 to +2. So, there are 5 solutions for m, okay. -2, -1, 0, +1 and +2. Okay. So, these 5 solutions have the following forms. Okay. The first one is when you have sources and sinks along the x and the y direction. Okay. So, you can have plus q, minus q, plus q and minus q. Okay. You have 2 sources of plus q, that means, and 2 sinks of minus q, that means that the net source is identically equal to 0. Okay. However, in addition you have 2 dipoles here which are actually in opposite directions. Okay. So, this dipole is in this direction, this one is in this direction. That means that if you go sufficiently far away, the net dipole moment is identically equal to 0. Okay. Therefore, the temperature field cannot decay as 1 over r square. Okay. The temperature field has to decay faster than that, because if you had a net dipole, the temperature would have decreased as 1 over r square when you went far away. In this case, the temperature there is no net dipole. So, the temperature field has to decay faster than 1 over r square. Okay. In this case, the solution for the temperature goes as 1 over r cubed, right, p 2 okay, m of cos theta times cos and sine of m phi. Therefore, at n is equal to 2, okay, the solutions are in the form of quadrupoles. Each of these is separated by equal length from the origin. Okay, the length of each of these from the origin is the same. Okay. In the case of the dipoles, we saw that we can have 3 different arrangements. One is the source and sink along the z, x and y axis. In this case, one can have 5 different arrangements corresponding to n is equal to 2 and m is equal to -1, -2, 0, 1 and 2. So, 3 of these correspond to the sources and sinks that are placed along the coordinate axis. Okay. Along the xy plane is 1. Okay. The other one is along the xz plane. Okay. So, this is q minus q. Sorry, this is q and q. Okay, the other one is along the xz plane. Okay. There is a third one along the yz plane. That is okay, so these are 3 along the 3 different planes. If you arrange 2 sources and 2 sinks equidistant from the origin along 2 of the axes in such a way that the net source is 0 and the net dipole moment is also 0. The other ones, there is one along the xy plane, but not along the axis. Okay. Okay, so, this is q minus q, q minus q. Once again equidistant, but not along any of the axes. Okay. And the final one has sources and sinks arranged exclusively along the z axis. So, these are the spherical harmonic solutions for n is equal to 2 and m going from -2, -1, 0, +1 and +2. You will note that these are actually reminiscent of the symmetries that I wrote for you a little earlier. Okay. these are actually identical to these solutions. Okay. So, y 0 0 corresponds to a source, okay. Y 1 0, y 1 1 and y 1 minus 1 corresponds to dipoles, combination of a source and a sink in the limit as the distance between the two goes to 0. Similarly, the orbitals, that is x y, y z, z x, x square minus y square and z square, correspond to quadrupoles. Okay. Quadrupoles, the combination of two sources and two sinks in such a way that there is no net source, no net dipole. The temperature field due to these decreases as 1 over r cubed. Okay. The next higher terms in the series are for n is equal to 3, and in that case there are 7 solutions for n is equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. 7 solutions called octupoles. They are generated by superposing 4 sources and 4 sinks in such a way that there is no net source, no net dipole moment and no net quadrupole moment either. The temperature field due to those decreases as 1 over r to the 4th power. That is, for n is equal to 3, the temperature field decreases 1 over r to the 4th power. So, the terms in the spherical harmonic expansion that we had solved by separation of variables are identical to the terms that you would get by having a single point source for n is equal to 1, a dipole for n is equal to 2, quadrupole for n is equal to 3 and so on. And if you recall, when we did the problem of heat conduction around a particle, okay, for a constant temperature on the surface there was a net source. Okay. On the other hand, we had solved the problem of the conduction around a spherical inclusion. In that case, there was a linear temperature gradient far away. There was no net source on the particle. Okay. So, the solution that we got finally for the temperature, we said that since far away the temperature goes as T prime r times cos theta, the temperature everywhere has to go as T prime r times cos theta. Okay. And from that we got solutions of this kind: A p n into r power n plus B p n by r power n plus 1, p n of cos theta. This A p n for n is equal to 1, it was equal to T prime, it was 0 for all other values. Okay. And so, the final solution for the temperature field that we got was of this kind in the matrix T is equal to T prime r p 1 0 of cos theta plus B m 1 by r square p 1 0 of cos theta. Okay. So, in this particular example, the temperature field around the particle in the matrix was the combination of the linear temperature gradient far away as well as this term here, which is basically a dipole term, okay, which is basically a dipole term. Okay. The particle itself did not have any net heat coming out. So, the source of energy within the particle is 0. The next higher term that can be non-zero is the dipole term. Okay. And if I plot the flux lines due to this dipole term, okay. So, there is a source and a sink which are separated by a very small distance, energy coming out of the source and going back into the sink. So, the flux lines that I will get due to this dipole look something like this. Okay. So, these are the flux lines due to the dipole, okay, which is aligned along the z axis. In this case, it has to be aligned along the z axis because that is the inhomogeneous direction. That is the direction along which there is a temperature variation. So, what I have basically done here in constructing this solution for the flow around for the temperature field around the sphere, I know that the solution far away has 1-0 symmetry, and because of that solution far away with 1-0 symmetry, I have flux lines which are a constant. If I did not have the particle, I would have just constant flux lines, okay, a linear temperature profile. However, I have a particle here as well, and I need to satisfy the temperature and the flux boundary conditions on the surface of the particle. So, I need to add a disturbance to the temperature field due to the presence of this particle. From symmetry, that disturbance can only be in the form of a dipole, and so I add a disturbance in the form of a dipole to the particle outside of the particle. Note that this solution is only in the matrix. I add a dipole solution outside of this particle in such a way, I choose the constant in such a way that the boundary conditions at the surface of the particle are satisfied. So that I get the correct temperature field outside of the particle. Okay. So, the combination of this constant temperature gradient and straight line flux and this dipole will give me the necessary solution which satisfies all boundary conditions. Of course, this dipole moment decreases as 1 over r square. So, I cannot use this within the particle itself, because at the origin itself r goes to 0 and therefore, this goes to infinity. So, this can be used only outside of an object. This is a decaying harmonic, it can be used outside of an object, and I add the constant solution and the decaying harmonic in such a way that I get the correct boundary conditions on the surface. If on the other hand I had a heat flux in the x direction or in the y direction, I would have chosen the appropriate spherical harmonic term that would have corresponded to a dipole along the x axis or along the y axis, okay, one of these two dipoles. And similarly, one can in problems which have the symmetry of quadrupoles, one can add the quadrupole term in such a way that one gets a correct symmetry. Okay. So, the flux lines due to a dipole will look something like this. The quadrupole, since it has two sources and two sinks, it looks something like this. This is for two sources and two sinks. Okay. And this, of course, these two are separated either along the x square minus y square as well as the z square. So, in this case alone you will get a linear quadrupole. Okay. In this case alone you will get a linear quadrupole. You get something that goes like this. Okay. Whereas in all other cases there will be planar quadrupole moments. Okay. And of course, in the case of octupoles you will have two sources and two sinks and so on. Okay. So, this is the relation between point sources and the spherical harmonic expansion. By suitable combination of point sources, I can generate the all the terms in the spherical harmonic expansion. Okay. So, it is another interpretation of the solution of the Laplace equation. We got this, the spherical harmonic expansion by doing separation of variables in a spherical coordinate system. I showed you that you get the exact same relation if you just superpose point sources. Okay. A source and a sink in such a way that there is no net source gives you n is equal to 0. I am sorry, the source and sink in such a way that there is no net source gives you n is equal to 1, 3 solutions, dipoles aligned along the x axis, y axis and z axis. N is equal to 2 is quadrupoles, there are 5 solutions, and the source temperature decays as 1 over distance. For a dipole it goes as 1 over r square, for a quadrupole it goes as 1 over r cubed, and that way you get all of the terms in the spherical harmonic expansion. Okay. So, to briefly summarize this section of solutions of the Laplace equation, you are basically trying to solve del square t is equal to 0 in some domain. One method that we used was separation of variables. In a spherical coordinate system, we separated out the variables into the r, theta and phi directions, and I showed you that just from symmetries you get discrete eigenvalues in both the theta and phi direction. In the phi direction, the solutions are in the form of sine and cosine functions. In the theta direction, they are in the form of Legendre polynomials. Then I defined a point source, which is non-zero only at the origin and is 0 everywhere else, and with a specified heat coming out per unit time. The solution of that goes as 1 over r, and that solution exactly corresponds to the solution obtained by separation of variables for n is equal to 0. Then we looked at n is equal to 1, and I showed you that the solution due to a dipole exactly corresponds to the solution for n is equal to 1. There are 3 solutions, dipoles along the x, y and z coordinates. N is equal to 2 corresponds to quadrupole, 2 sources, 2 sinks in such a way that the net source is equal to 0, the net dipole moment is equal to 0, because it's 1 over r cubed and so on, and higher terms. So, this basically covers the relationship between the 2 methods of solution that we looked at so far, separation of variables and the delta function solutions. Okay. So, this is all in the limit of very low Peclet number, okay, when we can neglect the convective terms in the equation. When we go to very high Peclet number, when we would expect convection to dominate, we will use other methods of solution where diffusion is restricted to small regions near the boundaries. So, we will continue this and then go on to convection dominated flows a little later. So, with this I complete my discussion of sources and sinks in 3 dimensions, and I will continue a little bit on Green's functions methods, and then we will go on to discussing high Peclet number transport. So, we will see you in the next lecture.